So we are going to start with an important theorem called as the De Morey-Laplace theorem, which basically tells that in an asymptotic limit, appropriate limit, the binomial random variable can be approximated as a normal random variable. Note that binomial random variable is a discrete valued random variable. Normal is the one is a continuous. By this, what we mean is, in order to compute probabilities related to the binomial random variable, under certain conditions, we can use an appropriate normally distributed random variable and find that probability. They will both be close to each other. So what we are trying to do is, let's look at a binomial random variable. It's a sequence of Bernoulli trials. Let's say we do trials, 10,000 trials, and then we ask what is the probability that x, the binomial random variable, which denotes the number of successes, okay, in certain number of trials, okay, is equal to 3000. Then we know the binomial formula, you have to use it. What is it? So let's say this is a Bernoulli trial and probability of success. Let's say is P. So if you want this, then it's given by 10,000 C 3000 and then P power 3000, 1 minus P power 7,000. So there is a formula, but these are all difficult to evaluate. So how do we go about doing this evaluation? This is where De Morey-Laplace theorem comes into play. So what it tells is, under certain condition, we can use an alternate method to evaluate these probabilities. We already looked at a Poisson theorem, which tells that again in the binomial case, when n tends to infinity, p tends to 0, but np is a constant, say lambda, then binomial can be approximated to be a Poisson random variable. That is, what we will go to is probability that x equal to k of a binomial one can be evaluated using a Poisson one, where np will be the Poisson parameter, e power of minus np power k by k factorial. This is a very good approximation. That holds good only when under this condition. That is, you treat, let us say, the number of events you want to evaluate over an interval, you divide into very, very small time slices, and the number of time slices in the limit it tends to infinity, and the probability that the event occurs in a very small time slice tends to 0, but that product has to be a constant. It's not just both these can arbitrarily, the limits cannot be taken arbitrarily. So then that n into p, if you call it as lambda, then this is the Poisson one. The other one important limit is the given by the De Morey-Laplace theorem. So what it tells is, when n tends to infinity, but p is finite, constant, such that npq root, okay, is in the neighbor is So NPQ, root of NPQ is in the neighborhood of NP. Then so what we can do is, what is binomial? Binomial of n comma p can be approximated as, can be found equivalent as a normal random variable with mean NP and variance NPQ. So here in this case, P should not be very small or very large. P should be a finite constant. Okay, maybe 0.3, 0.4, 0.5, whatever it is, but it should not be very small or very large. The reason it should not be small, that is one thing, then only this will hold good. If it is large, very near to 1, then Q will become small. Then this will not be finite. It will also tend to become 0. So this should be not be small or large, and it has to be in the neighborhood of this one. What we mean by that is, you find NP, I will show you here an example, and this should be that is, with respect to this value should be comparable. That's what broadly it means. So what, let's say we will take probability that in the case of this 10,000 trials, we want the probability that x equal to 4,000 is what we want to find. Then this is approximately equal to, see here this will hold good. NP is 5,000 and we can find root of NPQ. Let's not take 4,000, we will take 4,500 also. It will be in the neighborhood of. If you find NPQ, root of NPQ, you will find it will be 50. So it is, of course it is not very close, maybe I will even make it as 800 also. For in these cases, then it will hold good. Then instead of computing using this kind of a formula, you can use an appropriate Gaussian formula that do it. So where mean is NP and variance is NPQ. So 1 over root of 2 pi NPQ sigma square into e power of, I am not substituting n and p here right now. So this is what I will not to make it easy, even general. Yeah, this is then 2. Probability that x equal to x. It's that this is an integer because it is a binomial one. So can be found out using that. You evaluate. This is not this a probability. This is a density function. Actually, what will happen is in the neighborhood of this one, x plus dx. If you want to find this probability, so this density function into the dx is what is meaningful. Or even if you want to find this discrete probability, if you use this one, this will give you the probability. So what we have taken, this is the mean and variance is NP. For example, let's say and then fair coin, and then we are interested in finding probability that the number of x, okay, the random variable denoting the number of successes in out of 10,000 trials lies between So again, what we can do is we can find that you can find the CDF of this one. Okay, that is sigma k is equal to 0 to 5100, 10,000 k p power, like that you can put. That will get the CDF evaluated at this. Minus the CDF evaluated at this will give you this. Or you can simply do sigma k is equal to 4900 to 5100, 10,000 C k p power k 1 minus k power 10,000 minus k. That summation will also give you this one. But that's not very difficult to find. So we use this de Morey-Laplace theorem and then use a binomial approximation. So here what it means is that we will do the transformation of x being transformed to x minus mu by sigma to convert into a standard normal one. Here mu will be n times p, sigma is equal to root of npp. So in our case it will be 10,000 into 0.5, that will be 5,000, and this would be 0.25. Sigma will be, sigma will be 50. So I can, this is just I will do finding it. Now I will do a transformation, 4,900 minus 5,000 divided by 50 less than or equal to, same thing here also I will do. So same thing, inequality, nothing will change. By doing all these things, same property remains. But now, what I know is, now x is binomial, but according to this one, root of np cube, okay, is 50. That is very near to the mean. We are actually finding over 2 sigma around the mean. That's what we are doing. 2 sigma is 100, and that is what we are trying to evaluate. So the normal approximation is valid. We have to find the probability that the x takes a value plus or minus 2 sigma around the mean. But this is an arbitrary normal random variable. I want to convert the standard normal to evaluate this one. So we are doing this. So if you look at this one, this is probability that how much is this? Minus 2 less than or equal to, what is this one? This immediately becomes a standard normal one, y, and this is 2. We have to note it, y is 0, 1. Now that's it. I am just converted everything to evaluation of a probability or over a range of a standard normal. So that is given by CDF of 2. Well, by the moment I put this one, it is nothing but CDF of standard normal minus. That's it. Okay. So this is the de Morey-Laplace theorem and the corresponding binomial approximation for the normal approximation for the binomial distribution. Next. So we will dwell more into these concept of joint, marginal, and conditional probability density functions. These are all for continuous. As far as possible, some discrete also we will look into. So if we have two random variables x, y, the joint, we will just recollect the notations and so on, is denoted by this, and by that it means probability that x is in the neighborhood of actual this, by that what we mean by that, this is what it is. So what is the interpretation? So this is what we mean by the joint probability density function of two random variables x and y, and the corresponding CDF is the CDF. If you define a function g of x comma y is an ordinary function of two variables x and y. Now you can define a random variable, say z, which is connected to x and y random variables using this function. We will look at how to arrive at the density function CDF of z. We will treat z as a function of two random variables. We will do it a little later. But right now, if you want to find E of z, which is E of g of x comma y, we can do it as follows. What you have to do is, if you want to find the expectation, use the density function and then find it. The same way we have to do. We have a function of two random variables, integrating over the whole domain of the random variables. This function with the weight being probability density evaluated with x and y. So note all these things. These are random variables. While take expectation, it has to be random variables. But these are just values. And this is a function evaluated with two values into f. See, where you use capital letter, where you use small case, it's all very important. So this is how you can evaluate the expectation of a function of two random variables. Then the marginal density function of x, once you know the joint density functions, it can be found by integrating out the variables of not interest. That is, the moment we are writing it like this, we are telling that I don't care about y. Y can take any value. That is what it is implying. That can also, I can change it also. It's one and the same. It's not always true. By adding this condition, I am not doing anything wrong. So what I do, it's not the density function. Okay, it's not x less than or equal to this one. Okay, fx of x into dx. If you want, it is. This is what it is, interpretation. So if you want the marginal density function fx of x, what you will do is, that is, y has to be integrated out. You will get the marginal density function of x. Then we have the conditional density function. Okay? All these I mentioned in the earlier lecture. I am just summarizing it so that we are going to take many examples so that it becomes clear. That is f, x. We can condition on an even. We also looked at this. Okay? If you have one random variable x and an even, that is, what is the density function of x given that the event A has occurred, then what you have to do is you have to evaluate this. See, moment to density you cannot write a probability. That is the problem. You cannot equate a probability with this one. In order to equate, you have to put dx. The interpretation has to be there. You have to multiply it by dx, and here you can put a probability. What is this one? Density of x means this is one condition that has to be true. Another condition is A should also be true. This is P of A given B is A and B divided by P of A. This is how you interpret the conditional density function of x given the event A. Instead of event, we can also have a random variable. So, if x and y are two random variables that are joint density functions are given, is the conditional density function of x given the value of y. So, how do we interpret it? See, that actually can be written as fxy of x comma y divided by fy of y. Is the same thing. A given B is A and B by B. But this interpretation is right. Although these are at density, this interpretation is right. So, given that like that you can write, okay, but A given B I will immediately put it like this. So we will divide it by delta y on both the sides, and then we will take the limit delta y tends to 0. So here if I put this one, this becomes fy of y, and this becomes fx of x given y of x given y. That is, y takes the value in the neighborhood of y. Capital Y, the random variable, takes a value in the neighborhood of small y. With this being the condition, what is the probability that x will take a value in the neighborhood of x, small x, into dx? Okay, that is the interpretation. Then this dx and this dx can be removed. It's only for correctness sake we have put. Then this conditional density function is the ratio of the, sorry, this is not this one, x comma y. That is what this one is. So we can formally write this equal to this. Now we will take some examples. Well, suppose you have your home here, and then you go to a metro station, and then the train comes at fixed time. Let's say train comes at 7, 7:15, 7:30. Punctually it comes. You start walking down to this one, but your time, the time you reach here can be between 7:10 to 7:30. And it is uniform in this interval. You go, you wait, the moment the train comes, you board and then go. So you will be waiting for some time. We would like to know the distribution of the waiting time. Okay. So what it means is, my time of arrival is uniform random between 7:10 to 7:30, but the train comes at only 2. This is of no relevance now. At 7:15 and 7:30. If I go before 7:15, I will catch it. If I go after that, I have to wait till 7:30 and catch that. Okay. So now, what will be the waiting time distribution? It is now not going to be uniform. We can see that. First, we can take the two events. Event A, arrival time is between 7 to 7:15. B, between 7:15 to 7:30. Based on that, my waiting time will change. And immediately we can calculate P of A and P of B. What is P of A and P of B? Arrival time is uniform between this. This is 20 minutes interval. Okay. So this should be 1/20 and this is 7:15. Okay. Probably I arrive, this is 1/4. This is 20 minutes, this is my first 5 minutes. Probably I arrive in a time between, this one is 1/4. And this is 15 minutes gap, this 5 minutes interval, this 15 minutes interval. This is 3/2. Then if, what is the waiting time? I will call that as the W as the waiting time. It's a continuous random variable, W. What is the property of W? Okay, equal to W, okay, given A. Actually we have to find the density only, not the probability. Equal to does not mean, but we can find, okay, or FW given A of small w is what we are trying to find out. So given that A has occurred, what will be my waiting time distribution? It will be uniform between 0 to 5 because my time of arrival is like this one. Given that I arrive before this one, I have to wait. I will definitely catch the 7:15 train, and maximum I will wait for 5 minutes, minimum 0 minutes. It's uniform between 0 to this one. Then this is uniform between 0 to 5, and it will be like this. What is this? Given that I arrive after 7:15, what will be my waiting time distribution? It will be uniform between 0 to 15. We can write this one. This will be uniform 0 to 15. This is uniform 0 to 5. So that is actually given by 15. So then now what is the waiting time distribution? So we have found, what we have done is we have found the conditional density functions on two conditions A and B, which are mutually exclusive, collectively exhaustive. So Fw of W, the unconditional density function of the waiting time, is Fw given A of W into P of A plus Fw of small w given B into P of A. Again, this I believe I have mentioned, this is the total probability. This, because you put a condition, you get the density function. These are two conditions weighed by the corresponding. So this is very easy to find. So yeah, in this one, if W is less than 5, then what will happen? This one is what? This 1 over 5. For A, it is between 1 over 5 is this one, into the probability is 1 by 4, plus for this one it is 1 by 15 into 3 by 4. This is true when the waiting time is between 0 to 5. When my waiting time is above 5, of course it has to be between 5 to 50. Then if you look at this one, it is 0 for above 5, because given that condition A has occurred, I arrived before 7:15, I will never need to wait more than 5 minutes. Okay, so this is 0 for W greater than 5. So it is 0 into 1 by 4 plus this is still 1 by 15 into 3 by 4. Okay, so this is how I can find the unconditional density function. It will look something like this. For 0 to 5 it will be more, beyond that it will be less. The reason is there are two occasions on which I will wait less than 5 minutes. One in this place, one from 7:30 to 7:25 if I arrive. There also my waiting time is less than 5. So both of them will contribute to these cases. That is why it is happening. Well, now then we will take the next example. What you do is, you throw a dart on a target which is circular in shape. Okay, this is X, this is Y, and this is R. And let us assume we will only consider those cases when the dart hits the target, it falls within this one. I am expert in the sense that I will definitely make it so that it will fall in this one, and the probability that it lands in any one of the point within this one is uniform over the entire area of this circle. Okay. Then we have to find the density function of the landing point of the dart. That is, it will be a pair of x comma y. I have to give the density function for that, but it is random, anywhere it can land. So what I am asking is f x y of x comma y. It's only again, it's a continuous one. Definite point I cannot tell, but if you take any point and then find the neighborhood, I can tell find the probability by taking the density and multiplying it by this infinitesimal area around that. That will give you the probability. That is the interpretation. So this is what? It is uniformly distributed in this area. So it is just 1 over pi r squared, as long as x squared plus y squared is less than or equal to r squared, and it is 0 otherwise. This is what? The uniform distribution in a spatial, two-dimensional uniform distribution. Now what we will do is, we will now find the marginal distribution and then the conditional distribution, so to get a familiar of what it is. F x given y. Okay. X given y is equal to y. That is, if I say that y takes a particular value, this one, I was told that takes a particular means what? In the neighborhood of this one. Then what will be the density function of x? What will be the range x can take, and in that range what will be the density? So if you only take values in this slip, in this strip, its range itself changes. It is not minus r to plus r, it will be different. And again, it is not necessarily uniform like this. Sorry, x you are telling me. y takes a particular value, yeah, x takes a value in this one, it is not necessarily uniform. Don't get it, it's only the range. How do we find it? That is what we need to find out. For that, what I need is fxy of x comma y divided by fy of y I need. But first I have to find the marginal density function of y. Let us first find it out. Fy of y over y. That is, what it means is, given a value for y, it has to be minus r to plus r. Given a value for y, okay, what is the probability density in that neighborhood? To do that, I have to, that is the marginal density function of y, I have to integrate out x. This is what integrating y, x will give me y. So against what this one is, minus infinity to plus infinity is not required. Given that y takes a value small y, what is the range of values x can take? This integral outside it is 0, and fx of x comma y, this is the range over which the actual integration will take place, and the density function I have to put, which is constant, which is 1 over pi r squared. So wherever it's 0 I am not even integrating. In this one it's pi r squared into dx. That's all. So that is actually it's x pi r squared. This is fy of y. Okay. So, what can you tell about this? Is this uniform? Fy of y, is this uniformly distributed? Y, not y, y. Because y is there. It's a function of y. If it were uniform, it has to be a constant. So it is not like that. See, it should be something like this. See, when y takes a value here, x will be spread out. But y takes a value here, x will be confined. But values, for these values of x, all x's are allowed. For these values of x, okay, for these values of y, certain x's are excluded. So you can see that it will be more concentrated here. Am I right? Is the interpretation? This is how it will be. Now we will come back to this. So on the top we have 1 over pi r squared. So this is 1 over pi r squared. Here we have found out this one. So this is what we get for x. This is again not, we have to define the domain also. That is, it is to be x, should be mod x or something you can put, or minus root of r squared minus y squared less than plus root of r squared minus y squared. Only over this one this is so what we are telling, the conditional density function of x given y takes the value small y is given by this. Is this uniform or not uniform? I need an answer, yes. Huh? Why? No, from mathematically speaking first, and then we will go for interpretation. Huh? What I am telling, density function of x given y takes a particular value small y. So it is a density function of x. So variable x, you are plotting the probability of x against x in the x domain. Then y is given to take a particular value. Given that condition, is the density function of x dependent upon the x? No. Because here y is for a given value of y, this is a constant. So the density function of x is constant. That is, if from the moment I fix this one, then what? If I fix this y as y, then the density function it has to uniformly lie between these two. Okay? It has to be like this. If I take the value of y to be here, it has to be uniformly here. The moment I fix y, then x and y are totally random, anywhere it can occur. The moment I fix y and then tell that which value x can take, it can take any value in the allowed range, uniformly. So, the conditional density functions are all uniform. The other way for the x also. But the marginal are not like that, because you are taking uniform. The uniform has different range. And then you are multiplying it with the corresponding probability and then taking average to get this. That is why it becomes non-uniform. Because the weightage for all these things are different. And then you are adding it. Of course, these places will occur in all the places. So this is one more example. So then we will take the other things. We looked at the Poisson random variable. Okay. Let us say we have an interval over which some Poisson events can occur, and x is the number of events that occur in an interval that is given to be a Poisson random variable with the parameter lambda. We said discrete random variable. What do we mean by that? We will recall what it is. Probability that x equal to k, that is probability that k events has occurred. The random Poisson random variable takes a value k, is given by e power of minus lambda, lambda power k by k power k. This is the Poisson PMF. Okay. Now, what we do is, there are events that occur. Every time the event occurs, then what you do is, you classify that event into two categories based on certain criteria. So, an event has occurred, one by one event has occurred, you either classify it to this category or another category. And the probability with which you will categorize to this category, let's say call A and call category B, this is P. And actually this has to be 1 minus P. So every time a Poisson random variable, an event occurs, you just categorize into two categories with the probability P and 1 minus P. Now A, then you look at how many events A has occurred. A is again a random variable, B is another random variable. A plus B will put together the original random variable X. So what is the nature of A? Is it Poisson? If so, what is the prescription? PMF. how about B and so on. That's the question. Before that, an illustration of why this occurs. For example, the number of births that takes place in our city in a given day can be treated as Poisson random variable. It can vary, it can be 100 births today, tomorrow 90 births or something like that. So those are all registered in corporation, some this way. Then what we do is we just want to find how many female child, how many male child. So based on that, every birth you categorize into male or female with some probability. And then we ask, you have modeled the number of births to be Poisson random variable. Now you are looking at whether the number of girl child birth, is it still Poisson? If so, what will be the parameter for it? And so on. So this is what the number of accidents that take place in the city is some Poisson. You classify into fatal, non-fatal with some probabilities you found out, and then how are they? But again the thing is, the way you classify this event is independent of the way you classify this. They have no correlation. Each one is independent. And use the same probability P with this belongs to A category or 1 minus P belongs to B category. So this is what happens. This is called as the Poisson splitting process. The same number of it. You have packets to a network, you divide, put it in two queues with the probability P, 1 minus P, and send it to two routers. So many ways in which this Poisson splitting will happen. So this is what you are asking. Now, how do we find this? This is the original one. So instead of putting K, I will put N. Okay. Now, this is X, the original process. Okay. Then what we are asking is probability that A is equal to 3 is what we have to find. That is, what is the probability this A will take a value K? That is not easy to find. Okay, given. See, in all these problems you use the divide and conquer, or you simplify the problem, solve it, and then again go ahead and then get back to the original or the generalized one. You condition, put a condition under which the problem becomes solvable. Then you uncondition it and generalize it. So suppose I ask, what is the probability X equal to K given, A is equal to K given X equal to N? What I am telling is, if I tell you that N events have occurred here, what is the probability K events would belong to category B? If I ask you this question, will you be able to tell? I am giving you one, it may not happen, but suppose I condition it, that X equal to N, what is the probability that A is equal to K? How do you find it? What am I doing? Every event I am categorizing it into A or B with probability P or 1 minus P. So each one is a Bernoulli trial. With the Bernoulli trial, I put it in A or put it in B. N Bernoulli trials I conduct, and A is the number of successes that occurs, probability of success being P. So it is nothing but Nk P power K is 1 minus P power N minus K. Is it clear? That is, these are all N events have occurred. Each event, even by event, I categorize it into A with probability P and to B with probability 1 minus P. So number of events that will be categorized under P is given by this Bernoulli one. This is the binomial distribution. So this conditional probability mass function becomes very simple to calculate. Now I will uncondition it, but N, X can take the value N can be any given value that I have to account for. So probability that not this one, we are, instead of doing this one, this is what I want, I will find out this one. This is what we want. This condition easy to find. So how do we find the unconditional one? That is, if you find I will find this. This is the theory of total probability. That is k given n into x equal to m, where n can take value 0 to infinity. Is this clear? See, this is the conditional probability of A taking a value k given x equal to n. You multiply it by x equal to n, probability x equal to n. This is the only way. See, if this happens, it happens with the probability n, where x can take a value n, okay, with this probability, where n can range over this one. So I have accounted for all possible values of n. For each one, I have given a weightage of probability x equal to n and multiplied this conditional probability. So I am unconditioning it. Now there is no more n will not, everything has been taken care of in appropriate weightage. So this is how you find the unconditional probability given the conditional probabilities. Okay, so 10, just 2 minutes. So next, that's all. It's all next. It's now just algebra. So you tell me, n 0 to infinity I have put, but again certain things are not allowed. What I am asking is, given that totally n events have occurred, what is the probability that a k of them will belong to A? So here at least k events should have occurred. Then only out of them, if all of them can belong to A, means minimum of k events should have occurred. Then only you can. That is the best case where all of them go to this one. It can, n cannot be 0 and A cannot be k being greater. So it has to be k to infinity only. And this is what we have given. And what is this one? Probability x equal to n. It is the Poisson PMF. We have given e power of minus lambda power n by n factorial into n k p power k into 1 minus p power n minus k. So now what you will do is you will take out e power of minus lambda here, okay, and then lambda power n is there, p power k is there, okay. I will put lambda power k, I will take out. Then I will be left with lambda power n minus k by n factorial, and here n factorial divided by k factorial, n minus k factorial, and then what I have done, p power k, that also I will take it out. See, what I am taking out are all independent of n, so I am valid to take. Please note all those things. Into 1 minus p power n minus k. So lambda power k, p power k has been taken. What remains? Lambda power n minus k. E power of minus lambda gone. N factorial this one. So this we can again we can club it. See, this is where I think you will appreciate the beauty of Poisson exponential distribution. Everything will come out very neatly. If you look at the final formula, you will see what it is. N varies from k to infinity, it is n minus k, n minus k. So I can replace it by I varies from 0 to infinity, I. This is the exponential factor. What is this one? What is the summation? Correct. So e power of minus lambda, e power of plus lambda goes lambda p power k, and what happens? E power of lambda p by k factorial. This is what remains. This is property 838. Good. This is Poisson distribution. Where the parameter is lambda p. If it is alpha, alpha power k, e power of alpha by k factorial. So A is Poisson with parameter lambda p. So what happens? You have a Poisson, you split it into two, p and 1 minus p. What you split into p will be still p. The parameter will be lambda times p. Other thing will be lambda into 1 minus p. So the Poisson nature is preserved and easy to compute the parameter also. Okay, we'll stop at this.